Quick notes on adaptive beamforming. The general process is to take data from all of these various degrees of freedoms, in this case illustrated as being the outputs of the digital subarrays, and cross-correlating every stream of data with every other stream of data. And this requires that data from every degree of freedom gets sent to every other degree of freedom in some way, or to a centralized location. Once you do that, you can build up this covariance matrix that, once inverted and applied to nominal weights, gives you the actual weights that you'll want to apply to those degrees of freedom. The problem with this is that it requires lots of computation on the order of the cube of the number of channels that you're adapting on. And we've been looking at some ways to take that more down to the square of the number of channels using things like the matrix inversion lemma, and you can see the paper for details. But this continues to be a computationally expensive process. The other problem is that you need lots of quote-unquote all-to-all communication requirements. In other words, to correlate every data stream with every other data stream, you need to get data from every degree of freedom to all the other degrees of freedom. The nominal way of doing that is to take all of your pipes, your data pipes, into a single processor. And this of course, doesn't scale well if you get tens of thousands of high bandwidth data streams going into a single computational node, even if it's parallelizable in a physically small space. So there's been some interesting work looking at mesh-based beamforming, things like spanning tree concepts to optimally distribute processing throughout an array, utilizing the links available to you between front-end nodes in a mesh-based configuration. So this is one of the opportunities in the future for improving the game with adaptive beamforming in these systems. Point out really quickly, there's a good paper by Zatman, who was at Lincoln Labs at the time, talking about how to best choose degrees of freedom, or what each one of these dots represents. And I encourage you to look at that paper if you're interested in this. Calibration, I'll speak about briefly. Calibration refers to determining the fixed portions of front-end processing that maximizes beamforming performance to minimize the need for adaptive beamforming. There are a lot of different things to consider, whether you're calibrating in the field or in situ, or whether it's in an anechoic chamber or initial, whether you're using near or far field measurements, whether you're using internal calibration mechanisms or external mechanisms like a chamber or a far field horn. Digital arrays basically alleviate a lot of the issues associated with these in terms of the errors you can achieve, but they have some practical considerations. Like if you're building a digital array, you almost always need to be able to store element level data for calibration purposes, even if you are not sending every single element's sample to a final location. You can't just hook it up to a network analyzer and go to town like you could with an analog array. Instead, you need an auxiliary, you typically want to use auxiliary array channels to form a virtual network analyzer within the array. Finally, just speak to some important trends. Mention again that the more you drive down the cost of the transmit-receive modules and up and down converters behind each element, the more you introduce the potential for larger errors and temperature dependence and filtering related concerns. And in this sense, calibration is an enabler in getting rid of those errors. Initial or in situ calibration, I'll cover that briefly on the next slide, provide opportunities for array self-calibration, which can provide long-term maintenance and operation cost reductions. So there have been a lot of, well, not a lot, but a few different research groups looking at how to use the inherent feedback paths associated with having multiple transmitters and multiple receivers built onto an array panel. Basically looking at building up matrices of couplings from a group of transmitters to a group of receivers that can tell you about errors on these transmit elements and these receive elements and how they evolve over time. Here's a simple example from my dissertation where as an array heats up, you can see that one of the transmitters actually drifts over in phase as a result of being heated up literally by a heat gun. And this example shows that the array is able to self-calibrate and bring all the transmitters back into phase with each other and all the receivers back into phase with each other. There's also been some work looking at extending this to wideband equalization. You can see here errors on the order of 1% or 40 decibel level error based on a simulated wideband self-equalization. There's also the ability to detect for breakages or errors in the antenna S parameters, which is an interesting potential future self-diagnostic tool. So a simple example, as simple as can be, of how adaptive beamforming can be traded against calibration in terms of complexity at the system level. The overall idea being that one can simplify the need for adaptive beamforming with a large number of degrees of freedom by having a well-calibrated array that gets you most of the way there. So an illustrative example would be, let's say I want to steer a beam in one direction, say plus 30 degrees, while simultaneously steering a wideband null towards an interference source with, say, 16 elements. If you did this with a fully adaptive array using, for example, a 32-tap FIR filter at every element to impart true time delay and allow you to steer a wideband beam in the direction of a target without beam squint, that would require 512 degrees of freedom, which for each adaptation would take 4 gigafloating operations. So that's not per second, that's per adaptation. If you need to do that multiple times a second or every millisecond, it becomes computationally infeasible and scales very poorly with the number of channels and the number of taps. There's a way to do this a little bit better in the frequency domain, but you're still dealing with quite a number of processing, quite a bit of processing. A generalized side lobe canceller would instead take the signal from the desired direction and add to that, or actually subtract, a forward estimated undesired component in the direction of the null. So basically, steer towards the target and subtract off the small residual component that is in the direction of the interferer. One could adaptively determine these filter coefficients, HR, say with a 16-tap filter, and that would only require 150 kilofloating operations per adaptation. But to do that, you'd still need independent data. For example, with 16 taps, you'd need about 100 independent data samples. And independent data is not always easy to come by in the presence of coherent clutter and signals that don't have a large enough range. One could do this with calibration, having an extremely well-calibrated array where the response in the desired direction is precisely known, as is the response in the undesired direction. And one could tailor a specific receive filter that would dial in an exact cancellation of these two. And with mutual coupling algorithms, we mapped this to about 75 kilofloating operations per update to mutual coupling error estimates, or to equalization error estimate. Here's just a result of a simulation, steering in one direction while providing a null in another direction, and this is with perfect calibration. You can see this null goes down to the 70s of decibels. With 3% RMS element errors, which is typical of what you achieve with an analog phase shifter at every element, you would achieve nulls that are on the order of 35 or 40 decibels in the null direction, and this can provide a fundamental limitation with a barrage jammer coming from that direction, for example. All these errors can be mapped reasonably well using simple expressions that are derived in the paper. And just to give you an idea of what sort of calibration errors you can tolerate to get a given null depth, and with typical phased array, digital phased array errors on the order of 1%, you can provide nulls going from 40 to 60 decibels, and that's fairly good even for adaptive beamforming. So in conclusion, digital arrays promise to open new application areas, performance and flexibility. There are architectures coming out increasingly common for dealing with all the data. There are operational digital array systems out there, as well as a lot of future interesting test beds that are under development. And finally, enhanced calibration can not only extend the performance of arrays, but potentially reduce the cost of the electronics that you're allowed to use on these systems to open them up to a wider variety of application spaces.